divergence of magnetic field is 0. Which means what? There is no magnetic monopole. Imagine like you had only North Pole. A magnet that has only North Pole. What would happen? Just magnetic field would come out in all directions from it. And then you would have some divergence. We have seen that for any infinite wire with current I, if we take any loop around it of any shape, then this is true. Del cross B equal to mu naught J, right? We found this from B dot dl. We integrated B dot dl over this loop, and then we converted this to del cross B dot dA. A is the area covered by this loop, and then we found this for this identity. But this was, and the J comes from the fact that we took many such infinite wires packed so that there is a density of current. All right, so I mean, whatever. So your J dot dA integral was your total current enclosed. But this derivation was a special case with infinite wires, infinite long steady currents, not a general derivation for steady currents. In general, let's take a volume. So there are some volume currents inside. Okay, so three-dimensional volume and steady current flowing like fluid or whatever. So inside this volume, let's say, this is where all the sources of currents are. Here we can take an infinitesimal volume. So the current is really here flowing. This volume is d tau prime. And we choose an origin from which this lies at r prime coordinate. And we are going to calculate the magnetic field somewhere here, let's say. So this r is the position vector of the point where we are going to calculate it. While this difference is this vector. So r equal to r minus r prime. And so remember that the magnetic field is outside somewhere. It can be anywhere outside the source. So r is the position of the magnetic field where you are measuring. Well, r prime coordinates denote where the sources are, that is currents are. Okay? So there are two different things. Okay, so let me write the form of this. Mu naught by 4 pi d tau prime. So that's why we are integrating all the currents. So over the d tau prime coordinates. Okay, not here. So d tau gets only up to the volume where the current is flowing, d tau prime, and J is of course as a function of r prime, because that's where the Jr, this r prime varies, times from the charge, what is the distance? So that's why this vector. This is the magnetic field due to this piece. So that's why it's here, and the distance here. Okay, we understand every coordinate very well because this is going to be important. Okay. Now, if I say that I'm going to take a divergence of this, what I mean is this thing is over the coordinate x, y. So what r is, r we can write as x, x cap plus y, y cap plus z, z cap, right? While r prime is x prime, x cap plus y prime y cap plus z prime z cap. Two different places they are. And del is of course the gradient operator, which is del x plus y cap del y plus z cap del z in terms of Cartesian coordinates from last semester. So if I apply this on that, then these things are applying on x, y, and z. If you apply this on this, you get 0. Okay? Because this only x outside here, while the x primes are all here. So they're independent variable. Del x of x prime is 0. Okay? So this must be clear. So this when I apply this on here, this will get inside. This will not act on this because these are primed. Even this will not act on this because j is a function of r prime. But this will act on this because this has both r and r prime. So it will act on this piece only. Okay. Another interesting fact is, you know, so del is like, really like what you, in one dimension on this. So in 3D this, right? This 3D version of this. Take this thing, for example, del x of some function of x minus x prime. I can write this as also minus del x prime of the same function x minus x prime. It's clear, right? You take the derivative and you take the derivative of the argument. So here you get just 1. On the other side you have minus of x prime. So you take the derivative of this and then you take the derivative of this thing, x prime x on this, so minus come minus minus plus. They are the two same thing. So this thing is actually this vector, this difference vector, only the x component of it. So equivalence statement is when you apply this del on some function of r vector, then similarly I can write del prime on the same function r, where del prime is x cap del x prime, del y prime, del z prime. Okay, it will be useful later, but we can do that. We can convert this, and instead of now this acting on this, it will act on that, and a minus sign. So it's the same thing, right? Same thing, just like this. You do this, you will understand what I mean. So these are useful things. Maybe I could write them down somewhere. Del of gradient or curl or anything on some function of this is basically del prime on the same function as this. Okay. So let me first calculate the divergence of B, which means mu naught over 4 pi. It gets inside, doesn't act on prime. So it must apply now on what is del dot A cross B? B dot del cross A minus A dot del cross B. Anyway, so here your A is this thing and B is this. So if I expand, so J of R prime, R B vector 2 whole R cap by R square. So del cross A B is R by R square, A whole J R prime on Okay. This is 0. Tell me why. It's R prime. It's there. And so these are x prime, y prime, z prime function of. And this is del del x, del del y, del del z. Independent. So this is just 0. Just derivative of x with respect to x prime. This is identically 0. And this is 0, well, this you have to calculate. Spherical polar coordinates have you done? Right? In Cartesian coordinates, this was x cap del del x, del del y, del del z. In spherical polar, del of anything, let's say some t, is r cap del t by del r plus 1 over r, so theta cap over r, del t over del theta, plus 1 over r sine theta, phi cap over del del phi. This is the gradient in spherical polar. This is just gradient operator. So let me write it like this. Okay. So this is gradient operator, and a vector you can take. This vector has only r component, r cap over r square. It does not have any theta or phi. Okay. You can calculate. I'm not going to calculate that. That's a simple vector calculus. So please do it. Okay, please do it. Curl of this thing. Calculate curl of this thing. It will be 0. And from geometrically you will know. If you draw this, how will this look like? It's just all radial direction. So some things are function that is decreasing with radius, right? 1 over r square. And its direction is away from the radius. So it's like the electric field of a single charge actually, right? 1 over r square. So how does that look like? That looks like just lines coming out. If you take curl, what is the meaning of curl? It is the rotation. This thing has no rotation. It's just diverging in all directions symmetrically. So if you took any, path and did this dot dl integration, you will find that it is 0. Okay, and that's why the curl of this thing you will find, if you calculate explicitly, will be 0. So this is 0 because this is on r and this is r prime 0, and this r because this vector has no rotation. So the curl of this vector is 0. So that means del dot b is identically 0. Divergence of magnetic field is 0. This has a interesting physical meaning. So it means that, what is divergence? Usually you take a surface. Okay, you take a surface and this vector field is inside that or coming out, and you take any surface and you take a surface integral. That means you calculate the flux of this particular vector. It's called a vector field because it is a function of position and it's everywhere. Like electric field is a vector, but it's a vector field. B is a magnetic vector field. So if you take the divergence, the meaning of divergence is how much this vector field is diverging out of your surface that you have taken. Okay? And divergence 0 means whatever is coming out is entering again. So how much, as much as it is diverging, it's also converging into this surface. Okay? So physically some lines are coming out and exactly equal amount of lines are entering this surface. Any magnet. So if you know a bar magnet, right? So lines coming out of this, but then they're also entering through the the south pole. So if you are calculating how much lines are diverging from within this surface, obviously 0. Okay? While if you put an electric charge, that will not be 0, because it will be just going out in every direction. Okay? But that's not true for magnetic field. And turns out magnetic field, identically, divergence of magnetic field is 0. Which means what? There is no magnetic monopole. Monopole is like one pole. So electric charge is like a monopole, single pole. Okay? So like if you had, imagine like you had only north pole. A magnet that has only north pole, what would happen? Just magnetic field would come out in all direction from it. Right? And then you would have some divergence. That's called a monopole. Just like electric charge. So electric charge is like an electric monopole. But magnetic field turns out has no monopole, because only if it had a monopole there would be a divergence. Otherwise, no. It is at least dipole. Whatever comes out enters through the other pole. It is like similar situation in electric field will be, you have a plus Q here and a minus Q here. That an electric dipole. So if you had like this, plus Q and minus Q, this would be like similar situation. They will enter through. So they will start, lines of force will start from the positive charge and will enter and reach the negative charge. So then if you take a divergence of this situation, it will be 0. Okay. So this equation tells us that magnetic monopoles do not exist. And that's true. You break a magnet, it will become two magnets with north-south, north-south. You don't find, okay, south and the north. So it's mathematically consistent. We just proved that it cannot exist. If this is how you calculate magnetic field of a steady current, if this is given, then it implies that there will not be any magnetic monopole. So we need to calculate once again. This thing acts on R, not on R prime. So it will just cross the tau prime. It will be here, of course, but it has no effect on this coordinate, times R over R squared. So now we need another formula, del cross A cross B. Current of some, let's not write A, B, B is magnetic field, so some U cross B. So that is U del dot V minus U dot del V. For del cross U cross V, this is the formula. Okay. U and V, some vector fields. Now U here is this J. Let me put the J of R prime times V is this R cap over R square equal to, so J of R prime del dot v, this is V R cap over R square minus, so U is, so J R prime dot del, and here R over R square. That I must use here. This is the one. Okay, this, have you ever done this? Divergence of R over R square? Definitely did this. It's just Gauss law. Electric field of a single charge. How is it? Q1 by 4 pi epsilon naught R cap over R square. Divergence of electric field is Gauss law. How was it? Del dot E So integration d tau prime was just charge over epsilon naught enclosed. Okay, and charge enclosed we can also write as some d tau prime and charge density. Okay, charge density time volume, integration of that could be charge. So that will give you these, if these are, so enclosed charge means what? The surface that you are taking, inside that how many charges are there? Q1, Q2, Q3, so sum of all of them. If it was a continuous charge system, then you could just integrate those charges if you knew the charge density. Do you know Dirac delta function? Dirac delta function, right? It has some value at one point and zero everywhere. A strange function. So this thing, del dot r cap by r square. If you calculate it, if you put the electric field here, this term will appear, right? If you don't use Gauss law, let's say you don't use the Gauss law, you just integrate this thing. And I gave you electric field of a charge, single charge. And I ask you to do this. So you have to calculate this thing, right? Eventually, some Q1 by 4 pi epsilon naught. You can calculate that using the divergence, or just forget about that. Just not any prime. This is okay. This is okay. If you use the spherical polar coordinate, then let me just write down the divergence formula for spherical polar coordinates. It is 1 over r del r of r vr. So vr is the radial component of the vector v. Then some, okay, blah blah blah, theta phi terms that actually will not need, because your vector has only r component. Put that here. Oh, this should be r square. So if this is r square, you put r cap over r square. So what is your r component? Cap goes away, that's unit vector. It's just 1 over r square. We put it here, 1 over r square cancels out. And this is just 1, and then del r of 1 is 0. So you'll see that this is 0. But I mean, if really the divergence of this is 0, then this is 0 here. Then you integrate a 0, and that should be 0. But we know that's not 0. That's Q enclosed by epsilon naught. So what is going on? Gauss law is wrong. What did we do wrong? We wrote r square over r square equal to 1. So it's fine when r is not 0. When you can continuously, smoothly come to the origin. We always do this. For example, sin x over x. Limit sin x over x, what is it? Limit sin x over x is 1. So the limit must exist. This function, the divergence of this function. The divergence of this function really does not come to 0 in a smooth way. Because there is nothing anywhere, and there is something exactly where the charge is. So it's 0, 0, 0, and then you have a charge at a point. So this charge density is not continuously coming to 0. It's like a fixed charge at one point and 0 everywhere. As if like it has an infinite density at this point and 0 everywhere. That's the delta function. Okay. And in case of delta function, you have to deal with the mathematics of delta function. So this divergence of r cap over r square is precisely 4 pi three-dimensional delta. How do you define delta? You define in terms of integral. They are not like functions. So they are only defined inside an integral. So this means d tau prime del three-dimensional delta r prime, this thing is 1. When, if you include this origin inside the volume. So then this is the definition. This becomes 1. What is other? I mean, if you had a function like this, then what does the delta function does? Exactly at 0, this has a value. So the answer of this is f0. Just remember, this was the definition of delta function. So this is what I need actually. Divergence of r cap over r square is the Dirac delta function. Here we have it. Now, this del is del del x, del del y, del del z, and this r is x minus x prime, y minus y prime, z minus z prime, right? This r. This is the difference, r minus r cap. But then, del del x acting on x minus x prime is just equivalent to del del x minus x prime acting on x minus x prime, isn't it? This is just x on this and 1, and this one is 0. Similarly, this x on this and it's 1. So I could just write this equal to this. Is it clear? What we have here, we have some del del x acting on some function that has x minus x prime in it. And it's just, you can replace this x by x minus x prime, nothing will change. Because the other one anyway is going to give you 0. So you can do that. You can just replace x minus x prime equal to some what? T, right? And then d of this thing is just dt. And that's how you can replace this variable and you will get this. It's just a change of variable. What did I write? Del del x on some function x minus x prime is just equal to del del of x minus x prime. Is it convincing? I mean, just put x minus x prime equal to some a. What is it? And then this becomes just f prime of a, right? Or you could just take this, so this is f prime of x minus x prime. And what? Del del x of x1, and that is 0, no effect. So this is again f prime of a, right? So that's why. So which means I can write del dot r cap over r square and treat it like just r. And so this will become 4 pi three-dimensional delta of this thing, this result. And I need this result, so we can put it here. 4 pi del 3 of this. So this term sorted out, we need to find out what this thing is. In the end, we'll put it inside the integral. This term. So once again, we have del here, and here we have a function of, so it's a function of like x minus x prime, and we have here some jx del del x, right? J dot del, jx del del x, jy del del y, jz del del z. Let's say we have just x component, and so this is going to act on this function. This is equivalent to minus jx del del x prime of f of x minus x prime. Once again, just switch to that variable and the minus comes in front. Okay, so that means in 3 dimension I can write this thing as minus j of r prime. This delta I'll write as del prime. This acting on r over r square. Del prime is just del del x goes to del del x prime. Del del y to del del y prime, del del z to del del z prime. Why we need that? We need that to apply a trick that will help us so that we can use, it's called chain rule in derivative, derivative of some f into g. It's derivative f into derivative of g plus g into derivative of f. So that kind of thing we want to apply here. And that's why we need this x on this. Because here, del does not apply on this. Because del x on x, y and z, and this is x prime, y prime, z prime. But now it can, right? Now we have del prime. Shifted it. Now it can apply on this. And of course it applies on that because this has both x and x prime. Now we can apply the chain rule for simplicity. Let's just do with x component. So what is x component of this? Just del j dot j r prime dot del. This is of course fully a scalar. It does not have any component. So the whole thing. But this is a vector. Let me write this as a full vector divided by r cube. And so I can write just the x component, x minus x prime by r cube. Electromagnetic theory is a lot of mathematics. So you have to be good at it. And for that, you need to regularly practice. Derive all these things on your own. Okay. Again. Because reading, you will not remember and you will not understand. You really need to prove all these things on your own. Anyway, so this is how the x component of this looks like. And then if you apply the chain rule, so you need to do the x component of this, del dot of, let's say, x minus x prime by r cube and j of r prime. This is prime. If you expanded this, you will get, if you expanded this thing, you will get, so what was the formula for this formula? Divergence of, just tell me really. What is the formula for this? Phi del dot t plus t dot del phi, right? So phi del dot t plus t, so t is what? This thing. Del phi. So del of x minus x prime by r cube. So which one we need to replace? We need this thing. We need this thing. Which one is this? It's this one. I think that's how it should be. I think t dot del x on phi. T dot del x on phi. Yeah. So which one? We are expanding this thing. So we have this equal to this. And when we apply this on this thing, we get this. So we need to replace this thing using this formula. This one is this term. So this equal to this minus this. This is really what we need. We need to put this term there. And our r over r cube is just x component we are writing. So x minus x prime r cube on this thing. Now here, this thing, although it's del prime acting on r prime, it's still 0. But because of a different reason. We are working in steady current. Steady current means it's not changing with time. The charge densities are fixed. It's not like charge density is, reducing or increasing anywhere. So one condition for that is del rho over del p must be 0. So the charge density should not change. And if you remember, this is equal to 0. It was the equation of continuity, I said. It means that if charge density is changing somewhere, then that must imply that some current is going out. If you have some volume, if your charge density is increasing inside, it means some current is entering. If it is decreasing, it means some current is diverging out. So divergence of current is equal to rate of change of charge, negative. Okay? So this is negative, means charge density is decreasing inside a volume with time, and so some current is diverging outside that volume. Now, the condition is that steady current, so there should not be any charge density changing anywhere. So this is 0, that means this must be 0. And we are working in a steady current situation. Biot-Savart law applies to steady currents. So, this one. Okay, so this is 0. So which means this equal to this. So this term equal to this term. So this becomes that minus del prime dot for just one component I'm writing right now. So the x component, let's say, over r cube j of r prime. Okay, so from this I get j r prime 4 pi del 3r, and this thing is minus minus plus del prime dot minus x prime over r cube so only x component. So let's just prove this one to be 0 for x component, leaving this thing for later. Leaving this thing for later. So remember, this whole thing is inside the integral of Biot-Savart law. Okay? So this was del cross j cross r over r square. Going to put it inside that integral now. This part later. It will become easier when you do it once. So start doing it piece by piece. Maybe del dot b equal to 0, prove that. Okay, that will be easier. Once you do that, this will come like del becomes minus del prime and all this thing. At least once you do that, then go to the next step. And don't prove this. I need to, so I was supposed to finish this in one class. But then you can do it in piecewise. Like, just deal with one term today. Okay, once you get this term, then work on the next term. At least first get how to expand a term into chain rule. And then next morning, do the other one. But at least finish it once. This is absolutely necessary. I mean, this is the easiest mathematics probably in physics. You have to just practice yourself, build yourself. That mathematics, you should know better mathematics than any mathematics students. That's for sure. They know a small subset they will be dealing with, but you have to know all branches of mathematics. Anyway, these are this is just vector calculus. David Griffith's book, okay, for electrodynamics. First chapter is about vectors and then vector calculus, only these mathematics. So he will start with a simple thing, give you exercise, you have to finish those. So one semester of vector calculus, you should be now like quite an expert. And so based on that, this course was given for the second semester, you know. So once you know that course well, then this should be easy. But if that was not so well, then this is going to be hard. So that's why I'm telling you, your next class you have some time. DJ Griffith's electrodynamics. And do the first chapter, vector calculus, once again. Then the next class will be easy for you. Okay? So you have some, preliminary ideas. You did one semester on that. So it will not take much time, but do some exercises. It's absolutely necessary. Otherwise, really, you will hate it. This thing, I will show you later that this thing when integrated becomes 0. Okay. This thing when integrated becomes 0. And only this term will survive. And you know the integration of this thing, it's a delta function. So when r, what is r? R minus r prime. So delta of this times a function. So when r equal to r prime, this will come out to be j of r. And that will be your answer. Del cross b of r will become mu naught j of r. The one that we proved for a single infinite wire will be true even for a general steady current situation. Promise me you will go back and At least study this vector calculus chapter.